Thank you. So thank you for coming again. I'm going to discuss today the proof of the large deviation principles I gave yesterday. The proof is complicated, but the goal of the proof is not so much to show all the technical details, it is to show the ideas that go into the proof. And those ideas should be very accessible to you. And I'm going to try and do my best to go slowly and to show those ideas. And there's basically 6 ideas in the proof. I think it's important to look at those ideas because they are, on the one hand, very typical for the kind of things you have to do when you want to work with large deviation theory, and even though they are tailored to the problem that I'm dealing with here, they have a much broader level of applicability or generality, if you wish. And also they are the kind of things that you would typically run into if you want to do large deviations in some other kind of problem. Secondly, there are certain aspects of this technique that are really mathematically interesting and that merit spending some time on it. And as we discussed yesterday, there are 2 quantities to which this method can already be applied. And what Francis was asking last time and say, well, shouldn't there be a much more kind of classification possible? And I do think that that's the case. So I think the method could be applied to several other interesting quantities, and that will have to be part of the future. Now, the slides are available on the ICT website, so you're welcome to look at them also at some later moment. I've worked very hard to prepare them in such a way that you could even read them and understand them if I were explaining them to you. So they are intelligible on their own, and at least I hope so. Okay, now the core idea behind the approach that I'm going to discuss is that we're going to do some form of discretization. But it is not going to be a discretization where you say approximate Brownian motion by simple random walk on the lattice and take a very fine limit of a small lattice grid. That's not what we're going to do, because that would actually be in some sense too difficult. We're going to do a discretization in another way, namely we're going to follow the Brownian motion path and going to view this path as a succession of very short excursions. And then we're going to try and understand what the Wiener sausage does to a good approximation if I only know the beginning and the end points of these excursions. So rather than looking at the whole Brownian path, I only look at the Brownian path at punctuated times. And an important step in the argument would be, if you know these punctuated times, you have very good control of what the whole Wiener sausage is, because the excursions are short. And this is what we use the skeleton approach. And the reason why we're doing that is because understanding large deviations of these excursions themselves is something that fits much better into a standard large deviation theory as Donsker-Varadhan have developed them for Markov chains. Because these points that are the beginning and end points of successive short excursions, they form a Markov process of a very simple nature. And we are able to use then large deviation theory for Markov processes as a tool on our way to deriving the large deviation principle for the volume and the capacity of the Wiener sausage. So that is the take-home message, if you wish. So what are we going to do? Here is the list for today. I'm going to first focus on the volume, and our large deviation results said that if I take the limit of the probability of the logarithm of the probability divided by this fractal exponent of t, of the probability that the volume is below a certain number bt, and b should be any number, any positive number, but it becomes really interesting when b is below the capacity of the unit ball, that limit will be equal to the rate function, and the rate function is the one for which I wrote down a variational formula. And we're going to do this in two steps. We're first going to prove that this is appearing as an upper bound, so that if I take the lim sup of the quantity that we're interested in, I get the minus the rate function as an upper bound. And then this will require a big part of the lecture of today. Once we're done with that, I will be very easily able to convince you that the lower bound is also true. So that also the lim inf of this will be greater than or equal to minus the same thing, and then we would be done. Okay, and as part of the proof, we will have to see that the variational formula that I had presented yesterday for this rate function is indeed coming out as I wrote it down. And towards the more later part in the lecture, I will go and see how this method, the skeleton method, and the ideas that went into proving this can actually be transferred to the capacity. And as I have explained to you yesterday, the capacity is a very different quantity than the volume because it's a much more non-local object. Now the proof comes in 6 steps, and I've listed them here, and this will keep us busy for about an hour. There will be first a notion of compactification. We're living in RD, and we have to somehow go to a large approximation of RD, some very large box. And we will have to argue that, okay, that's okay when the box becomes very large. Then I will introduce this skeleton idea, so breaking up the Brownian motion into a succession of many short excursions. Then I will try to write down a formula. I will write down a formula for this probability in terms of these excursions. Then I will argue, and this is something that I call concentration of measure. I will argue that when the excursions become very short, knowing only the endpoints of the excursions will allow me to get a very good approximation of what the Wiener sausage is. Okay, and that's because the Wiener sausage has a finite radius. Then we will be in a setting where we can get out a big hammer from our toolkit, namely the Donsker-Varadhan large deviation principle for the empirical measure of a Markov process, and apply that to the expressions that we will have then derived at that point. And then we are left with a somewhat complicated analytic expression, of which we have to take a limit when the excursions become very short, and then this complicated looking expression will reduce to something much simpler, and that will exactly bring us to the rate function that we're looking for. And then finally I have to say, okay, I did this all on a very large box. Now what happens when the box goes to infinity, because I was originally living on RD and not on a big box in the lattice. So those are the steps that we will have to go through, and each of them is a little story. What I will do is to give you the main ideas. I'm not going to write down the whole proof in detail, but I'm going to give you all the key steps and make those steps intelligible for you and make them plausible. And whenever there is a point where you say, look, okay, here is actually a somewhat delicate point, but never mind, it's okay. I will point out to that so that we keep it all on a human scale. Okay, so let's start. The first part is compactification. So what I do, I pick a positive integer, n, and eventually this n will have to be very large and will have to tend to infinity, but for the moment it's a finite number, and I just take the box of linear size n. And then what I'm going to do is I'm going to wrap the Brownian motion around this box. But what I do is I do not I'm not going to wrap it around this box. I'm going to take a box lambda m, but I'm going to still look at its blow up on scale t to 1d, 1 over d. So it's a very large box that is, n is fixed, but t will be growing. And I'm doing this because this was the time scale on which my Swiss cheese is living. So I do want to look at a large box, but on the time scale at which things are really happening. So I take this box, n is fixed, and t is fixed also, but t will go to infinity, and then afterwards n will go to infinity. And I'm wrapping my Brownian motion on this box. So when the Brownian motion would be leaving the box, it's going to come back at the other end. So I'm periodizing the Brownian motion. An important observation is, if I do that, then, and let me call the Wiener sausage associated with this periodized Brownian motion. If I do that, then the volume goes down. Right? Because when I periodize it, it could be that certain parts of the Wiener sausage that would otherwise be outside the box get mapped on top of a part of the Wiener sausage inside the box. So the wrapping has the effect that it will lower the volume. That is good because we're going to try and get an upper bound on our probability. So the probability that this is less than or equal to bt will certainly be less than the probability that this will be less than bt. So that is what will happen. Okay, right. And then once I have done this wrapping, I'm going to apply Brownian scaling. So I'm going to say, this was my box, but let me now scale the whole problem to become a Brownian motion that is really living on this finite box. This you can do by simple Brownian scaling. So if you multiply time by something, you have to multiply space by the square of it. In fact, it is a very simple observation to see that this quantity here, this is for the wrapped Brownian motion on this bigger box, is in law equal to the volume of a Brownian motion living on the smaller box, but with a much smaller radius. So by space-time scaling, and you can do it on a piece of paper for yourself, this object is equal in law to that object, and that object is a Brownian motion on this small box running up to a time tau, and tau would be, after you've done the scaling, t to the d minus 2 over d. But because you shrink the box, also the radius of your Wiener sausage will shrink with it, and the shrinking in terms of this new parameter tau will be tau to the minus 1 over d minus 2. So what happens is that we have bounded the volume of the original Wiener sausage by the volume of the Wiener sausage on this large box, and then we've scaled everything down, and here the radius was 1, and here the radius becomes a very small thing because everything shrunk. Okay, and these scales have been chosen such that they exactly fit what we're after. We are after proving that this probability is going to decay with this power. So the fact that we find this back here means that t is now really the scale on which we are looking. So tau becomes a new kind of time horizon. So this power of t is a new time horizon, which we call tau. And we are running the Wiener sausage over this new time interval, so in this new time range. And it so happens that the Wiener sausage is actually becoming very small. So this is what we call the shrinking Wiener sausage. So what is the result of me having done that? The result is the following. The probability that, so this object was smaller than that object, so the probability that of the event that I was looking for, the original Wiener sausage of radius 1 on the full RD, the probability that that's less than or equal to t will be bounded from above by the probability that the Wiener sausage on this object here is below b, and therefore and now the whole and now you see that there is no t here anymore. Now everything is in terms of a Wiener sausage living on a finite box with a different time parameter, tau, and I want the volume of this to be below a fixed number that is no longer growing with t, because everything is living now on a finite box. So here I want actually the volume to be less than or equal to b. So all I've done is obtain an upper bound by going to a large torus and then scale things down, and I'm faced with a problem that is now living on a finite torus, and two things have changed. There's a new time scale, which I call tau, and the radius has shrunk accordingly. Okay, so we have to study now the Wiener sausage on a finite torus with a radius that is actually shrinking with the time horizon. Okay, and this is a compactification trick. If the torus will later become very large, I should not have lost a lot by doing the compactification, but we will have to worry about that later. And the advantage is I'm now talking about a Wiener sausage on a finite torus. And that will be very important for applying large deviation theory later, because large deviation theory works much better on compact spaces than it does on non-compact spaces. Okay, so we have here a radius r tau is tau to the minus 1 over d minus 2, and time horizon is tau. Okay, now I can now set the two targets that we have to prove in order to complete the proof of the upper bound. We have to prove that for this shrinking Wiener sausage on this torus, if you divide by 1 over tau and you take the logarithm, then we end up with a rate function that is very similar to the rate function that we had, except that the world is not RD, but the world is lambda n. And indeed, we will do that. We will derive, we will show that this thing, which is an upper bound for the original downward large deviation, is indeed going to be given by a variational formula of exactly the same type as we saw it on RD, but it will be living on lambda n with a periodic boundary. And then afterwards we will show that the variational formula that we derive for this object on lambda n will simply converge to the variational formula on RD. So this will be a kind of analytic argument. And then if you put proposition 1 and 2 together, you end up having this upper bound, because this shrunking Wiener sausage was only providing an upper bound in for this probability event here, as I argued with this formula. And the nice thing about this is that now we have a new time scale, and this time scale, the large deviations in this new time scale are now really going to be exponential in that time scale, which is also good because most classical large deviation theorems come where you have to pay linearly, exponentially in the time scale. Yes, Alex? Yeah. Yeah, in fact, the first, I have already done one step, so we will need the next 4 steps to prove this one, and this is the decompactification indeed, so that will be the very last step. Okay, and in order to prove, so in the next 4 steps, I'm going to build it around 5 lemmas. And these lemmas are the key, are the backbone of the whole argument. And then once I have these 5 lemmas, we will be able to very quickly get to this result here, including finding the right variational formula for the rate function. Okay, so let's go to the second part, which is this excursion proposition. So now we're embarking on proving this first proposition. N is fixed, so the box is there. We're not going to change that box anymore. It will stay fixed until we get indeed to this very end, which is this decompactification argument. And what I'm going to do is I'm going to pick an epsilon positive, which we think of as something that is small, and that will later go to 0. And we're going to just look at our Brownian motion at the multiples of time epsilon. And I'm just recording what these endpoints are. Right, so on here I'm having a Brownian motion and I'm just cutting it up into pieces of length epsilon. And I'm only recording what these points are, and I'm not, in this skeleton, not keeping yet track of everything that is in between. And this is what we refer to as the skeleton. And I'm going to try to argue that when you know the skeleton and epsilon is small, you have very good control of the whole Wiener sausage. Now, how does that exactly work? Okay, I'm going to introduce a notation. If I write E of tau epsilon, it means that I'm going to take the expectation over everything that is in between the excursions, conditional on the skeleton. So if I fix the skeleton and I would take an expectation over the Wiener sausage in between, so as a function of what's happening in between, then I write that as a conditional expectation. So here it means you've averaged out the volume and you have and you only keep track of how this depends on this fine skeleton. Now, I should be carrying around this n everywhere because n is fixed, but I'm not going to do that because it would mean that I'm going to have to hang on, you know, add this index n on all the formulas, and I'm not going to do that. So the n is suppressed everywhere from the notation for the argument that we're doing now, but it is there. Everything is really living on this finite torus and n is kept fixed for the next you know, until we have managed to prove proposition 1. Now, what I'm going to do is to introduce the empirical pair distribution associated with the skeleton. So I'm going to write down an empirical measure. So what is written here is a probability measure. And I do this by just looking at the successive pairs of the endpoints of the excursion. So I'm going here and I say, what is these 2 points? What is these 2 points? What is the next 2 points concatenated? And I'm putting I'm putting here the Dirac delta. I'm summing all these measures up and divide by the total number of excursions. And what I then get is an empirical distribution that simply keeps track of the frequencies at which I see certain pairs of points that are the beginning and the ending of an excursion. And that's what we call an empirical pair distribution of the skeleton. This is an object that lives in the space of probability distributions on lambda n cross lambda n. So maybe I should write that down here because it's an important object. This will be an element of the probability distributions on lambda n cross lambda n. Right. Okay, and empirical distributions will be very important because what I can now do is to write the expectation of the volume of my Wiener sausage conditioned on the skeleton as a function of this object. So I'm arguing that this conditional expectation given the skeleton can be completely written as an explicit integral with respect to this probability measure that depends on the skeleton, because it's only the skeleton points that come in here. If you give me the skeleton, this is a deterministic probability distribution as a function of the skeleton. And once you know that, I can give you what the volume of the Wiener sausage is given the skeleton. And let's do that. So what would this be? This is the integral over all of your torus of the probability given the skeleton that the point x is in the union of the Wiener sausages that are associated with each of these excursions. So each excursion here, let me blow up this piece here. I have here beta I minus 1. Sorry, this should have been epsilon. I'm sorry, this. And the next one, the next time, then there's an excursion in here. I'm only keeping track of these points. This has this Wiener sausage around it. It has a very small radius r tau, and this is what I call the Wiener sausage of the ith excursion. And so the union of these Wiener sausage of the ith excursion are exactly my total Wiener sausage. So if x is in the total Wiener sausage, then I count, and otherwise I don't count. And indeed, that's the way how I get the average volume conditional on the entire skeleton. Now, what is very important to note is that these pieces of Wiener sausage between the different excursions are independent, given that I fix the skeleton. So if I fix the skeleton points, This is simply a Brownian bridge that in time epsilon has to run from here to there. So, given this whole skeleton, this is a Brownian bridge of length epsilon between the endpoints. And the endpoints are given once I have fixed my skeleton. Yes? This is a conditional expectation. This is an expectation when over the whole Wiener sausage, given that I fix the skeleton. Yeah? So this is still a conditional probability that I fix the skeleton. This is only a statement about the average volume given that I fix the skeleton. Okay, and then later I'll start to average over the skeleton. The probability that X is in the set, if I integrate this over the integral, if I integrate this over the whole box, I get the average volume. So if I'm basically integrating the density of this Wiener sausage conditional on the endpoints, and if I integrate this density over the entire box, I get the average of this object over the whole box. Is that clear? This is a conditional probability given, so I'm fixing the skeleton. So this is the conditional expectation given the skeleton. So I can say, first give me the skeleton, then let's take expectations but fix the skeleton, for fixed skeleton, and then later we can see if we can average over the skeleton. Yes? Excursions, yes. The number of excursions, because the total length is tau, the excursion length is epsilon, so there are tau over epsilon excursions. This is a probability measure that puts unit mass on the point which has these two coordinates. It's a Dirac measure that puts the unit mass on these 2 points. That's how you define empirical measures always. Right? It's a pair of points. I need to keep track of the pair of points because otherwise I cannot say that these two Wiener sausages for different excursions are independent. They have become independent because I fixed their endpoints. So if I take the next Wiener sausage around the next excursion, this would be Wi plus 1, then I claim that this is a random set and that's a random set and they're independent because I fixed these 3 points. So they are independent conditionally on having fixed the skeleton. They are not identically distributed. They have a different distribution because their distribution depends on what these 2 endpoints are. And of course, also here, this is happening in this part of the space, that will be happening in another part of the space, but as random sets, they are independent, not identically distributed, independent, given the skeleton. Okay, so the whole trick here is fix the skeleton, and then let's see what is happening. Yeah? For the moment, we don't need that yet. This is true in any dimension, and the fact that we would need d greater than or equal to 3 is only going to come later. So this works in any dimension. Now, since these sets are independent, they're not identically distributed, being in the union. So I can write this as 1 minus not being in the union. So 1 minus not being in the union. And if x is not in the union, that's the same as saying it's not in the first, not in the second, not in the third, etc. And since the WIs are independent sets given the skeleton, that probability will factorize into the product of the probability that you're not in the first times the probability that you're not in the second times the probability that you're not in the third. And I should say conditional probability given the skeleton. And then when you have the product, you write it again as 1 minus the probability that you are in this set. Okay, so this is an important fact. Here we have used that conditional on the skeleton. The Wiener sausage are independent. They're not identically distributed, but they're independent. And now I can write, I can raise this product to an exponential and then having a sum of the logarithms. And then the probability of being in the Wiener sausage, that point x is in the Wiener sausage, I can write down as an integral that involves this empirical pair measure. And that comes from the following picture. I'm introducing an object that says a q tau epsilon yz, which is the probability for a Brownian bridge starting at y and ending at z to hit a ball of radius tau around the origin. So I'm saying what happens when I have here a point y, here I have the origin and I have a little ball of radius rt around that origin. And I am an excursion that has to go from y to z. What is the probability that that excursion will actually hit this ball of radius rt around the origin? And let's give that a name. So this is a standard Brownian bridge probability. So that you will, okay, and then I claim that in terms of that quantity, this whole object here can be written as in terms of this empirical distribution. And why is that? You say, well, let's look at what the ith excursions is doing. It is starting at the point beta I minus 1 epsilon, and it ends at b y epsilon. Let's call that y and z, because this empirical distribution is picking up how frequently this pair is hitting the values y and z. And if that is happening, then for each of those excursions, the probability that that excursion will hit that a point x will hit that excursion. You say it's an excursion now that goes from y to z, and the probability that that excursion will hit the point x is as if I have this problem where this would be x, and this would be y minus x, and that would be z minus x. So if I start from a point y minus x, and I want to go to the ball centered at x, and I want to end up at z minus y, then exactly that is the event that my ith excursion, the Wiener sausage of my ith excursion, does contain the point x. So I'm able to write everything. Okay, yeah, much better. I'm able to write everything in terms of this empirical distribution that basically keeps track of how often I see points, beginning and ending points of the excursion near the points y and z. And if each time that happens, this is the probability that that excursion will contain, the Wiener sausage will contain the point x, and that's exactly that. This factor tau over epsilon appears because this object here times that is really counting how often it is happening, and therefore in here I'm really counting how often that is happening, so I must multiply by tau epsilon in order to really count all the excursions properly. Right, and the fact that there is a logarithm here comes from the fact that I had something here that I first had to raise to an exponential in order to bring the product in. Okay, so what do I have? I have an empirical distribution for the endpoints in pairs of the excursions. That is a nice object because it's well described by the Donsker-Varadhan large deviation theory, as we will. Given that you fix the skeleton, you have also fixed this object, and once you have that, the conditional expectation of the Wiener sausage just becomes a completely explicit integral with over that pair measure of some functional that actually is just an object in itself that involves Brownian motion of length n having to go from y to z and then having to hit this RT ball around the origin. So this is nothing mysterious. It's a standard object, standard Brownian bridge function that is appearing in here. Okay, so that we have written this as an exponential functional of this random variable living in the space of probability measures on lambda n cross lambda n, and it involves some standard function. And I'd like to already observe that since this ball has a very small radius, the fact that it has a small radius is that we sort of were scaling down to a finite scale, causes that this is a very small probability in dimension greater than or equal to 3, because if you want to travel from a point to another point and you want to hit a very small ball somewhere, this probability is small. So this logarithm actually will already become essentially linear. So we will soon get rid of this logarithm, and basically what will be, there will be a minus sign in front of the minus sign will go here, and basically you will just have an average of this standard Brownian motion function with respect to this empirical pair distribution of the excursions. So life is getting a bit simpler as we go along. But this is an important step where you have to realize that you can express this conditional expectation of the volume in terms of the empirical pair distribution associated with a skeleton. Okay. Now, why is this quantity very important? So you're saying, well, you were after understanding the volume of the Wiener sausage. Now you have derived a nice expression for the average of the volume given the skeleton. But isn't that average troublesome? And the answer is no, because there's concentration of measure. Alex?
The previous formula is exact as well.
It's exact. No approximation.
And it's explicit.
It's explicit.
Where is the difficulty in computing it at that stage?
Because the difficulty is in several points, as you will see. So you will have to, I'll come to that. So it looks nice, but you cannot immediately apply large deviation theory to it because you have to do some work. Okay. Now, there's a very important lemma, and that's a lemma about concentration of a measure. It says, if you will let tau go to infinity and epsilon go to 0, so you're looking at many very short excursions, then this conditional expectation given the skeleton will be very close to the actual volume. And that comes from the fact that the excursions are very short. If I punctuate my Brownian motion with very many short excursions, this whole discrete skeleton should be a fantastically good approximation of the whole Brownian motion itself. And therefore, the conditional expectation given the skeleton should be very close to the object, to the unconditional expectation at all. So when you have a very small excursions, your excursion skeleton should be such a good approximation of the whole Brownian motion itself that the volume associated with the whole Brownian motion should be very close to the average volume given the skeleton. And indeed, there's a key theorem that says when epsilon goes to 0, you can hardly distinguish between the two. And in fact, the probability that these two would be different by any positive delta is actually going to be very costly on the exponential scale tau. So we can basically forget, because of this property, that what the conditional expectation given the skeleton that we have computed, that would be any different from the two full volume as a function of the full path. And this is basically a proof that comes that uses concentration of measures argument. What you're using is that the this should have been v tau, so there's a typo here. There should be tau. The fact that the volume is the volume of a union means that this function is a Lipschitz function of these random sets. And then there is a very general theory by Talleyrand, which also in the meantime has even been more refined, that if you have Lipschitz functions of ID random objects, then the probability distribution of those objects are very sharply concentrated around their mean. Basically almost of a Gaussian type, and the concentration is very strong. So I'm not going to go into the technical details. For instance, this requires several pages of really writing out, but the idea is very general and doesn't really use much properties of the Wiener sausage at all. It's a general phenomenon for concentration of measures for Lipschitz functions of random objects in a much more general space. Francis? They're not identically distributed. Yeah. Exactly. So indeed, if you read the proof, it is several pages, and you need to go through all sorts of, unpleasant truncations and limits. But indeed, so there is more to it. But the juice is exactly in this Talleyrand concentration of measure estimate. Yes. Exactly. Right. So you need something about the tails, but it's very unlikely that the tails are too big. So in fact, we're using upper estimates on moments, exponential moments, which we know because of that these have been obtained in the past with rough estimates, and they're not unrelated to the upward large deviations. But okay, let me not go into detail. The key idea is this Talleyrand concentration of. So what this says is the object that we have just been computed is a fantastically good approximation of the object that we're after. Good news. So with the thing that we did here, we're on the way of computing the right thing. Okay, we're now in a situation where we can start to apply the Donsker-Varadhan large deviation principle, and this empirical pair measure is a very nice object. It satisfies a large deviation principle on the set of probability measures on my torus with rate tau and with a certain rate function that is just given by a relative entropy. So this is standard fact about if you have a Markov chain jumping around on a compact space. It's irreducible, it will be uniformly ergodic, and if you want to know the empirical pair distribution of where this Markov chain is, that's just given by a relative entropy. So the probability that this thing is close to mu is the relative entropy of mu with respect to something, and the something by the general theorem is, say, take the left marginal, and then apply the transition kernel of the Brownian motion here. So if I'm just interested in the empirical distribution of these points, then take the measure, then take the left marginal, and then propagate this left marginal with the heat kernel over a length epsilon, because that's what Brownian motion is doing here. And this is standard. This is part of the very first series of papers that Donsker-Varadhan wrote about large deviations for Markov processes. So we know what large deviation principle this thing satisfies. It's a completely explicit large deviation rate function living on this space. It's a relative entropy. You have to put an epsilon over here because time is only epsilon for a single excursion, and you have to propagate this with the heat kernel, or the epsilon time epsilon Brownian kernel. So we do know what are the large deviation principles of this object, and if nothing much would be to it, we could then say, okay, now let's use Varadhan's lemma and understand what the behavior of this object was. But we're not quite done with that, because this is small, this will vanish, and it will scale in a certain way, and I have to pass to a limit epsilon, and this epsilon has to somehow be absorbed into here, and there's another epsilon here, so we still have to pass to the limit epsilon and see what this will eventually come out. So Alex was correct, we are close to being able to apply Varadhan's lemma, but not quite yet. Okay, now the second lemma is that this object, which so well approximates the volume by this concentration measure, is satisfying a large deviation principle with rate tau and with a certain rate function, and the rate function is simply the rate function for the empirical pair measure. Take the infimum over all possible pair measures subject to a certain constraint, and this constraint is given by an explicit integral that would involve this mu. That is an integral like here, and that involves a new function, which is an object that is written here, and this is in essence the Brownian bridge crossing probability. So that's what I'm going to argue, and once I am here, I will be in a much better shape, because I basically then have an explicit variational formula where nothing is random anymore. I've used my large deviation principle, and I have an explicit function here, and I'm just supposed to take the infimum of this object here under a certain constraint that is completely explicit in terms of the measure mu and some function here. So we're going to try and argue why this is true. And the key observation is that this probability to hit this ball, which was the key object that appeared in my representation with the empirical measure, is going to be essentially 1 over tau. It's small, essentially going to be 1 over tau kappa times kappa d times this Brownian bridge object. So the probability that this event is going to happen in this Brownian bridge YZ is approximately given by this expression. And for that, this is basically a fact. I'm not going to go into the details of that. This is basically a very standard property of Brownian motion. If you want to say what is the probability that you will hit a very small ball, well, then that will be because of the way the radius is tau to the minus 1 over d. That will be proportional to t, and the proportional constant is exactly this factor here, because what this phi is that you say what you have to do is that you have to first, in some time before epsilon, end up here, and then in the remaining time you have to go back. And because this is a Brownian bridge, you have to normalize it by something here. So this is about getting to the ball, this is then getting back to the point z, and this is because you are looking at the Brownian bridge, and this integral tells you that you can hit this ball anywhere between time 0 and epsilon. So, okay. So indeed, since tau is going to infinity, this is a small number, so we were right in linearizing the logarithms. And I have stated that this approximation is uniformly good, and the uniformity is between quotation marks, because what actually happens is that this is not quite correct when these points are very close to this ball or very far away from this ball. And so I do need to do some appropriate approximations to make this work, but that is our technicalities, and I'm just not discussing them. Okay, so what do we have? We have, we're trying to go here. So I know that this object here is now scaling in a nice way. It will cancel this tau, and it will replace it by a kappa d. And then I know what the large deviation rate function was for this thing. And so what I end up with is indeed this LDP, where tau times q has been replaced by kappa d times this phi. And I've used the large deviation principle so that I say, if you want your volume to satisfy the constraint that it is equal to b, then this integral ought to be equal to b, because that was the integral that appeared in my expression for this quantity here. So we have now a completely explicit variational formula involving a known function, a measure in a nice class, and the rate function is this relative entropy. Now we're going to pass to the last thing to simplify this expression to something even simpler, and that is I'm going to look at the left marginal of this empirical pair distribution. So this is the object that only tells you the empirical pair distribution of single points rather than pairs. So if I define the left marginal like that, so it's take the infimum of the rate function for the pairs such that the left marginal is something. Let me call that the rate function of something. Then what happens is that this object has a nice shape. It's the shape as we want it in our variational formula. Namely, if you take this object, you divide by epsilon, and you take epsilon to 0, you end up with exactly the rate function that we're after, which is this Dirichlet form associated with Brownian motion. And that comes about using the following. There is a representation formula for the left marginal of this pair empirical measure, and this can also be found in the papers by Donsker-Varadhan. So if you want to know the empirical measure of a Markov process on a compact space, then you have to take this infimum here. So this formula is not exact, but as epsilon goes to 0, it will become much simpler. The fact that this is so you take this object, and you can prove by convexity that this is a subadditive function. So certainly this limit here exists. And to actually identify it, you basically, what you do is you go to the formula for this thing here, and you look at what this object here, this is the heat kernel does for very small epsilon. And if epsilon is very small, you can approximate the heat kernel by something very much simpler. And in the end, you see that this rate function for small epsilon becomes much simpler. It's the Dirichlet form associated with our Brownian motion. Okay, so if I put that all together, then I am going to end up with a formula. Sorry, I'm going to end up with a nice formula. And in order to put that formula down, I'm going to take two more steps. I'm going to approximate, sorry for the back and forth here. I'm going to approximate this functional by something much simpler, by saying if epsilon is very small, what does this thing become? And so I'm going to approximate this function by something simpler, and that function will be called psi of epsilon, by using that epsilon, when epsilon is getting very small, that this object becomes very simple, using the short time approximation of the empirical distribution. And if I do that, it turns out that if I take this integral, which is even more simple, here is just the heat kernel and a measure living on lambda n. If I define this object here, then we can prove that the function that appears in my variational formula is very close to this simpler function when epsilon goes to 0. And it's just coming from linearizing this phi epsilon, this Brownian motion kernel. And in fact, but let me not go on this. What you can do is you write the difference as a difference of two integrals with exponentials, and then a difference of two negative exponentials is bounded by the exponential of the difference. And then it turns out that you can just estimate this thing by something very simple, the mu minus its left marginal times the heat kernel, and then when you let epsilon goes to 0, then by an inequality that Andrea yesterday had on his screen, the Pinsker's inequality, that this can be bounded by this pair distribution function, and whenever this is finite, whenever 1 over epsilon times this is finite, this means that this is sort of order epsilon, and so this is getting very small, and therefore this is getting very small, and that's why this difference is 0. So you do it properly, and I put a little exclamation mark here by saying, okay, again, you have to worry about what happens when this rate function is very large, but never mind. So what we have is that we have replaced our complicated functional by a somewhat easier functional, and finally I'm going to replace that functional by something even simpler, and that is, if I take this integral, I take a function on the non-negative function L1 integrable on the torus, and I define this functional here, then actually this functional of the measure nu is very close to this function for this integral here for the function d nu dx. And again, that's the same thing. You write them out both. They're both exponential objects, and you again bound them by something that involves a total variation. And again, by Pinsker's inequality, you can prove that this object here goes to 0, and therefore this whole integral will go to 0. So these are, I don't expect you to be able to follow all the details here. You're welcome to look at the slides and to look at it a bit more in detail. But these are basically entropy inequalities. They're inequalities that you use in information theory. And because the rate functions that are appearing are entropy-like, or relative entropy-like, you have to deal with such inequalities. Is the mic still okay? Better? Yeah. Okay, so now we're ready to get to the end. And now I'm going to use an argument that is very, very common in large deviation theory, where we can apply all the lemmas that we've derived to get to where we want. We say, let's look at the exponential growth of some moment-generating function of the volume that we're interested in, where f can be any test function that you like. It has to be bounded and continuous. I claim that if I know this for all f's, I know the large deviation principle, as I will say at the end. So, what would this limit be? By the concentration lemma, this Vt is very well approximated by the conditional average, given the skeleton. So, I can replace this by that, provided I put the epsilon limit, an extra limit epsilon in front. Okay, that's the first lemma, the concentration lemma. Then we said we derived an LDP for this object, and it had to satisfy a certain constraint, and there was a rate function that was the empirical pair distribution rate function divided by epsilon. So, if I apply Varadhan's lemma, because this is a bounded continuous function, this inner limit over tau will become the supremum over all possible measures mu of this rate function for the empirical measure times the function, the f at the phi u epsilon, because this appeared in the constraint for the, this was a constraint, the constraining function in the rate function for this object here. Okay. Then we showed that the phi epsilon was very close to the psi epsilon. So that was the fourth lemma. And then we proved that if I, now this is still a supremum over double measure, but I replace it by a supremum over the left marginal, because this thing only depends on the left marginal. And this became very simple when epsilon goes to 0 as a function of its left marginal. That was this I1. And so I'm having a simpler variational formula that involves a single nu of an f of an explicit object and this rate function here. Now let's see when we go on with that. We said, oh, that now we pass to the limit epsilon going to 0 and said this thing was fantastically close to this gamma function of the d nu dx. This was getting very fantastically close as epsilon goes to 0 to the I function. So we end up with a limiting variational formula, which is the supremum over all probability measures on lambda n of f of an explicit integral involving the derivative of the density of nu times this Dirichlet form. And then we can reduce this to saying, let's call the derivative of d nu dx, let's call it phi squared. Then we're just taking a supremum over all phi's that have L1 norm 2. And then I see the phi appearing here. And that's what I get. So my lemmas have told me that the moment-generating function for an arbitrary f of my volume is given by this variational expression here, where here I have my Dirichlet form, and here I have the f of an explicit function of phi squared, which was the integral over dx of 1 minus kappa d phi x squared. And now we're done, because there is an inverse Varadhan's lemma, which is called Bridges' lemma. And this says, so Varadhan's lemma says, if I have a large deviation principle and have a rate function, I can tell you what the exponential growth is of all sorts of exponential expectations. Bridges' lemma says, if you know the growth rate of all sorts of moment-generating functions for arbitrary f's, then there is a unique large deviation principle associated with that. So it gives you a way to go back and forth. Varadhan's lemma goes from right to left. Bridges' lemma goes from left to right. So it's a kind of dual world that you can either work with large deviation principles or you can work with moment and generating functions. And this variational formula, since it's true for every f, will tell you that the volume satisfies the large deviation principle with the rate function that I gave. You may optimize over phi in here. You have to take the minimum of this object, but it has to be under a constraint that this integral has to be the b that you want to be at. Okay. The last thing is we have now proved proposition 1, so we've got the upper bound on the large torus. Everything okay. What happens when the torus goes to infinity? Does the variational formula on the torus converge to the variational formula on the whole lattice? And the answer is yes. And that requires just looking at the variational formula itself, using that the functions appearing there are convex functions, doing some very rough approximation thing. So this is a very simple an argument that is just thinking about analysis. Okay, you need to have something. Okay, so then once we are done now, we are done and actually saying, okay, we have proved the upper bound. Okay, I'm going to very quickly tell you how we get the lower bound. Yes? Just, yes, because the large deviation principle of Donsker-Varadhan really requires some strong uniformity to be able to apply it. And if you would do it on RD, you would not be able to do it. Okay. The lower bound really is nothing new, because I'm going to do something clever. Remember, I started with the Wiener sausage in all of space, and I wrapped it around the torus, and then I said, when I do that, the volume will go down, so if I study the wrapped Wiener sausage, I get an upper bound. Now, I can also get the lower bound by saying, when your Wiener sausages, when your Brownian motion gets out of the box, kill it. Then certainly the volume that I get by doing that will certainly be less than that of the full Wiener sausage, because it doesn't get any chance of creating a Wiener sausage outside the box. So by using killing boundaries rather than periodic boundaries, I'm going in the opposite direction. So I get a lower bound by killing the thing at the boundary. So what now happens if I do everything I did before for periodic boundary conditions, but I just do it now for killing boundary conditions? Works perfectly fine, because all the computations I were doing were completely local and looking at what was happening in here and how I would manage to hit a very small ball somewhere locally. If I'm not close to the boundary, I won't even notice that I'm actually living on a finite box. So what you do is you can simply say, if I put in the killing event, then conditioned on this killing event, I will just get the same variational formula, but now it has a killing boundary. And all I have to do is show that this killing event is not doing really very much. And that's because the probability that it will go out of the box has an exponential rate with a Dirichlet eigenvalue of the Laplacian on this box. And it so happens that this Dirichlet eigenvalue is tending to 0 as the box goes to infinity. So the cost of doing this is minor. And once I'm on the event that I'm killing, I just get the same variational formula with the killing boundary. And then all you have to show is that if you take the box to infinity, it doesn't matter whether you were dealing with periodic boundary conditions or killing boundary conditions at all. So again, you have to get back to the drawing table and do that. Whew. I know you are tired, and I'm tired because this was a very complicated proof, but let's step back for a second. So what have we done? We have gone through several approximations. Bring it to a finite box. Then periodize things, or do killing to get upper and lower bounds. Then do a skeleton. Then make the skeleton very fine, so that if you know the points, you know very well almost what your Brownian motion is doing. Then average over the Brownian motion in the excursions. You get technical formulas, but don't be shocked about them, because you can apply standard large deviation theory to those objects. You have to work a little bit so that you can actually do that. And finally, you're left with objects that are variational formulas involving relative entropies, but as the excursions get very short, all these formulas seem to simplify and simplify and simplify, and in the end, you're ending up with a palatable expression that somehow is doing the job for you. So that is how we went from the whole continuum, Wiener sausage on the whole continuum infinite space, to very core objects that standard large deviation is able to deal with. And then, okay, we have to struggle with some, sometimes exotic looking formulas, but they simplify a lot as tau gets very large, epsilon gets very small, and in the end, you get what you want. Okay. Now, I have only 8 minutes left, and I'm not pretending that I can do a lot for the capacity, but I just want to give a few hints of what is really different when you go and try to do this for capacity. We're going to follow the same approach, the same 6 major steps, but I'm going to just go through them very quickly and say, here it's the same and here it's different. And this is work in progress, so we're still struggling with making this work. The scale at which you live is different. It's no longer t to the 1 over d, but something much bigger. So I'm going to periodize around a much larger torus, and so again, and what I'm going to do is I'm in fact not going to periodize, I'm going to reflect at the boundary. Because if you periodize, the capacity is not monotone under periodization, but it is monotone under reflection. If I take 2 sets, and I take a line and I reflect everything with respect to this line, then the capacity of the union before and after the reflection is ordered in this way. Capacity goes down when you fold the space. You see this immediately from the variational formula that I wrote down in the first lecture for capacity. So we don't, yes? Yeah, so you have to take a d minus 1 dimensional line and flip the entire half space over. And so you don't want to periodize, you want to reflect. So now I'm going to reflect my Brownian motion into this box. So it says if you come here, you're neither killed nor you're appearing here. You're just, if you would like to go out, you're actually going to reflect, right? And then again, you get a bound in the right direction, and you can again do the old scaling as we did it before, and everything basically boils down that you have to look at a shrinking Wiener sausage, where now, however, there is a different space scale, there is therefore also a different time scale, and also the radius of this ball has to be changed differently. It's not d minus 2 anymore, but d minus 4. And again, we have an upper bound as before, and from now on we can suppress the index n. Then again, The old players come into the game, these same objects here. And again, there is concentration of measure because also capacity is a Lipschitz function of the WIs. And so the concentration is still something that you can do. You have to go through a few other estimates to do that, but that still works. So both step 2 and 3 are the same. Step 4 is a bit more complicated. I'm looking at my time, so what happens is that I have to, what I do is that I say, okay, my Wiener sausages all have a very small radius, so this union is very close to a disjoint union, because I'm trying to have Wiener sausages who have a tiny radius. And if they're all disjoint, then I can say, what is the probability that an auxiliary Brownian motion starting from a faraway point y will hit this union? Well, I can distinguish between which of the ith Wiener sausages it hits first. Okay, and here I use the representation formula for capacity, saying the capacity of a set is the probability that I hit this set starting from very far, provided the very far is scaled away here, and I multiply by the capacity of the unit ball. So the capacity itself has a representation as a limit of something involving an auxiliary Brownian motion coming from far hitting this object. And I'm going to distinguish again against which of the Wiener sausage around in the skeleton is being hit first, and then I'm conditioning on the winner to be the ith, and say the winner here is the ith, and what is then the probability that I actually made it from outside through this Wiener sausage without hitting all the other excursions and hit the ith one first. Okay, I'm going very quick now. Then I'm going to reverse time. I said I wanted you to go from here to hit the ith Wiener sausage without hitting any. We reverse time and say, rather than going from a faraway point to the Wiener sausage, let's go from this Wiener sausage back to the time point. And this you can do by time reversal, and you finally end up with an integral that involves a probability distribution on the surface of the ith Wiener sausage, some object that is actually related to the what is called the harmonic measure, times the probability that when you start on the boundary of the ith Wiener sausage and you are conditioned not to return to that sausage at all, that you manage to forever escape all the other Wiener sausages too. So you start at a Wiener sausage in the middle, you condition on never coming back to that piece. What is now the probability that I will actually be able to escape to infinity without ever hitting all the other Wiener sausages as well? And then, in terms of that quantity here, you have a very simple formula that just involves the capacity of a single Wiener sausage. This thing, by reverse engineering, scales in a very simple way. And for this, I use the law of large numbers for the Wiener sausage, for the capacity of the Wiener sausage. And then when I stick that in, I basically have to deal, I get a more palatable quantity that involves the empirical pair measure and something that is just a problem about Brownian motion managing to escape from the Wiener sausage starting from somewhere in the center. And then you go through, and I'll skip this now, you can read it later. You finally end up with the variational formula as we had it before, applying the large deviation principle for the empirical measure, which is appearing in here. This is a standard object that you have to analyze, in particular its scaling, and then if you apply that, and again use that, as we saw, this applies, the large deviation principle was given by this Dirichlet form, then we end up with the variational formula. So, in some sense, very simpler, But so we've come to the end and see that the same method can in principle be applied to the capacity again. Life is a bit different, scales are different, space-time scales are different, you have to deal with different objects, and in particular because the capacity is more complicated, you end up in your variational formula with a more difficult analytic object, which was the Schrödinger equation that you have to solve. But in the end, you get the expression that we want, and that was my goal. So thank you very much for following the main line and the big ideas of this picture. I hope you've got the gist of the picture and some of the key tools that go into it. They are very general, they're very powerful, they're very important in large deviation theory. And never mind the technicalities. Most of what was really necessary was there, and you can look it up in more detail on the slides if you want to. So, thank you very much.
Thank you. Questions? Alexandre?
How do you see the cheese? The Swiss cheese?
The Swiss cheese was that finally you are living on a box of size t to the 1 over d. What is the volume of this box? T. I have only time t available, so if I can never fill this box entirely. So because I'm on space scale t to the 1 over d, the Wiener sausage can never fill this box because asymptotically it's like, well, it's going to be bt. And so if b is smaller than the volume of lambda d, I'm going to get holes. And in fact, what will...
Because you know that you're still uniform on the box.
No, on this box you will follow a certain density profile. Near the origin, the density will be higher, close to the boundary of the box, and on d, if you're far away, it will be very small. So what you will actually get is a Swiss cheese. It's an object that has a positive density everywhere. It's a random object, we believe, and it has holes of size 1 in there. And as you're close to the origin, you only see small holes, and as you get further away from the origin, the holes get bigger and bigger. And so it's actually a kind of raclette cheese that has holes everywhere, but the holes get much bigger and more frequent as you go out.
So on the way to your proof, you have just proved also that for a finite box for both periodic, reflecting, and absorbing boundary conditions. So how does these three large deviation? I mean, they are different or same for finite but large n?
Finite and they're different. There's a difference between killing, periodic boundaries, or reflection. You get 3 different variational problems because they have different boundary conditions. But as you make the box tend to infinity, all 3 of them will go to the same limit. Yeah.
Like if I look at a time scale which is of the order of n square, and then ask how does the volume behave, like time goes to infinity, because I guess in that case when I keep a finite box and take time to infinity, in 2 cases it will fill up.
Well, you have to see that this was a scaling picture of something that was actually here. So what I'm actually studying before I do the scaling is the periodic boundary on a growing box.
But suppose I look at the finite box.
Okay, but that happens after I do the scaling, and then also the time horizon comes with it and goes from t to tau. And then I can study on that finite box. I'm just asking up to a certain time horizon, which is now tau, what is the probability that you're able to fill a certain fraction of the box? And that will depend on the boundary condition, but the effect will be minor when the box is very large. And this you have to prove. You have to prove that the rate function is converging to, they're all 3 converging to the same limit as the box gets large. and of the rate function. So if you want to ask other questions on that finite box, so if you would like to say, well, what more can you say than the large deviation, then I would have to go back to the drawing table and...
For example, if I ask the heating equals to the boundary, it will be...
No, because things would be weighed by this weight factor that is in the variational formula. So I think these things can be answered, and it's a good question, because if you would really like to prove that the path is really doing the Swiss cheese conditional on the volume large deviation, then you will have to start to worry about such finer issues and saying how is the convergence actually happening, and what are the error terms. You have to then peep a little bit beyond the large deviation scale and see what is happening. It shouldn't be well. It is doable, and I know in France there's a whole group of people who now are committed to doing that. Francis is involved that, and then Amina Sela, and Perla Souzi, and Bruno Shapiro, Quentin Berger, Julien Poza, various other people who say, well, shouldn't we be able to push this a little further to really get that, to prove the Swiss cheese? Whereas for me, the Swiss cheese was an interpretation, and finally the theorems were only about a large deviation weight function, nothing more and nothing less. Yeah. Yeah, so you can certainly say any strategy where you would have the wrong phi, the wrong drift, would be too unlikely. So the minimizers are unique modulo shift. So, but the step would be, if I know densities, do I know the process itself? I think it is doable, but you do need to go to some length to prove that.
When you go from volume to capacity, is there a problem with the concentration step?
No, there's not. I mean, you have to be that concentration is okay, because again, the capacity of the union, if you compare it with the capacity of the single sets, has a Lipschitz property. It is a bit more technical than the volume. So and as I said before, if you really go down to doing it, you need to do some truncation and let the truncation go to zero. But in principle, it should be okay. You look worried.
No,
but
the volume is clearly Lipschitz in the, if you take a curve and you replace by a nearby curve the volume of the sausage within the but for capacity it's not so clear.
No, if your set would be very weird, I could have a problem. But my Wiener sausages are all nice, compact, connected sets. They're not too big. So the class of sets for which I'm asking this is not too wild. And yeah, if you give me two awful fractal sets, then this would not be so obvious at all, because capacity is not a continuous function. I mean, I must have situations where the capacity of the interior of the set is the same as the capacity of the closure of the set, and that is true for the Wiener sausages. Okay, does that put you at ease? No, good point. There are issues here.
Methodology that you have laid out here, the 6 steps seem quite general, but in carrying this out for the upward, perhaps there is difficulty because this will give a variational formula for the rate function, etc. For the upward, that's not even known. You mentioned for volume, upward LDP for the volume. Yeah. So where is the difficulty in carrying out this program?
The difficulty is that the upward large deviations are controlled by a completely different mechanism. Whereas the downward large deviations are controlled by the Brownian motion saying, okay, I'm going to stay confined to an admittedly large box, but not everything. I'm not going to just go off. I'm going to try to make my life happen here. So it's sort of contracting. Now, if you want an upward large deviation for the volume, then what happens is that you can either do a strategy where the Brownian motion races off to infinity so that it basically becomes a long cylindrical tube and it makes really its volume sort of very large, but that's very expensive. What happens is that the rest strategy is that everywhere it blows itself a little bit up. And so now the variational problem is that you have to look at all stationary ergodic processes along a tube and then inflate those a little bit and then optimize over that. So it's going to be a horrific variational formula. I think we have a rough idea about what we should write down, but it will be an awful object about which I cannot do any nice analysis. Whereas the variational formulas here are neat. They're just classical variational formulas to which you can apply classical techniques and Sobolev inequalities to work with. And I don't know how to do that for this sort of supergalactic object that you would have to write down for the upward large deviation. So the upshot is they're controlled by completely different mechanisms. They have different costs. And the upward one is not... we haven't been able to write something down that you can analyze in any decent way for now. And that will be the same for the capacity.
Other questions?
One last question, maybe. Is there a relation between all those shapes and mechanisms and the blob picture for polymers, for weakly interacting polymers? You know, the Rausser model? Because the shapes kind of look the same. Even in the larger volume case, those excursions plus blobs.
Certainly. Those are models where you know, instead of having a Brownian motion and a Wiener sausage, you have some Brownian motion or maybe somewhat extended object that starts to interact with itself. And then it should fit into this into this kind of picture. So, for instance, for polymers with charges, we have a way of viewing this kind of picture. It should be very close to what you get for the Wiener sausage. Well, there are interesting challenges that you are looking at, which also have to do with bringing in some Poissonian obstacles and only sort of seeing them, making them random. And so there are lots of other questions around, and the polymer questions are discrete versions of problems that are similar. Like here, there is some global effect of the path. Like for the capacity depends on the whole thing, because everything interacts with each other. And so there is much more out there to which you could hopefully apply this. But you must climb steep large deviation principle hills. And they're beautiful. They have beautiful views.
Other questions? Francis?
The large deviation that you get at the end is a contraction of one which is at a higher level. So you know, you have some information on the density of populations at different radiuses. So do you have, can you extract more information out of that?
Yes, a bit you can do. So, for instance, I could say any strategy, any path that does not create an empirical density that is very close to that of the minimizer, we can kick out. And the Swiss cheese is doing that, but maybe there would be other strategies that would produce the same thing. So it could be that you could say, okay, I can have a local deformation and you won't see that on the scale that you see. So the answer is the true process is the Swiss cheese plus noise that isn't too costly, that I can never sort of filter out when I look on the scale that I'm dealing with. If I take a process that is just doing completely the wrong density profile, I can kick this out immediately. So I do have information about density, frequencies of empirical distributions of the winning strategy. But to then say, can you exactly describe how this Swiss cheese, because it's random, it will have random holes. Well, what is this distribution of the size of the holes? I don't know. But there are constraints.
But for instance, once you are at the right scale, you have information at which rate the density decays.
Yeah.
It's not compact.
It's not compact, no.
This scale it goes up to infinity.
Yeah, but it goes up to infinity, it's living everywhere, but it gets very, very thin outside. And you can, in principle, write down a one-dimensional radial differential equation for this density, and in principle you could solve it if you want to. It's a nonlinear equation, but so you can get a lot of information about it, tails, etc. So there is much more that you can pull out of the large deviation principle, which I didn't do, but it's there and can be done.
Other questions? If not, let's thank Frank again.
Well, thank you for listening.